Here we have two congruent circles. Notice half the circle is blue and half is orange. We're going to open up that one on the left, and we're going to rearrange those pie pieces like so. Kind of looks like a bumpy parallelogram, doesn't it? But let's put that back and let's actually cut that circle up into a little bit bigger number of pieces, say like this. And let's do the same thing. We'll take those pie pieces called sectors and we'll put them together like this. Interestingly enough, notice the greater number of pieces I cut it into, that parallelogram looks flatter and flatter and flatter until we get, like, as the number of sectors approaches infinity, that parallelogram looks more and more like a rectangle, doesn't it? And the area of that circle right here on the right is actually the same as the area of that circle on the left. So how could we find it? Let's see how we can reason with this here. I mean, this distance from here to here, isn't that the radius of the circle? From the center on out, right? And look at this. Of all the pieces of the circle, half of them are blue, half are orange. So all those bumps on the right side, isn't that really half the circumference right there? And if we let the number of pieces approach infinity, I would have to say that the area of that circle should roughly be approximately half the circumference of the circle times the radius. So length times width gives us this, doesn't it? And again, if we let, again, that's an approximation because we have a finite number of sectors. But as we let the number of sectors approach infinity, right, that gets more and more and more approaching the true area of the circle. So if we think of circumference here, circumference is really 2 pi r, isn't it? 2 pi r. And we could take those 2's and cancel them, like so. And pi times r is, yes indeed, pi r squared. So the area of a circle is pi r squared.